Today we're going to look at stereo nets. Many of you have probably never even heard of these before. I know the engineers, depending what classes they've taken or are taking, saw them last week. But this is something that we use in structural geology and in other things to look at three-dimensional planes, like a bedding plane, lines in 3D, such as like the hinge line of a fold, or a streak that's on a fault plane that tells you which way the fault actually moved if it wasn't, just a straight down or straight up. It could be a dinosaur bone. It could be a linear mineral. All kinds of different things that you need to be able to map in 3D space. And probably most of us are not awesome at 3D drawings. So it's good to have a different way to express it visually. Plus, later we'll find out that we can actually use it to calculate things without ever using math. Kind of nice. So stereo nets. What they are is a standardized way to portray a 3D world on 2D paper. Different than maps, because a basic map is just a surface, the surface of the Earth usually, on a flat piece of paper. This is something inside the surface, usually. We can use it to show a bed, a dike, a cleavage plane, the intersection of planes, like a fold of a hinge, the linear objects or minerals, striations from fault movement or even glacial movement, or even oil wells. You could map an oil field, all the different oil wells at different angles on one of these, and see if there are patterns or whatever you were trying to see. So what are they? Well, most of you have one in front of you already, but this is what this looks like. The one you have is a lot finer detail than this. This is every 5 degrees. Yours is every 2 degrees, so you can get more precise with it. But that net in the background is the stereo net. It's, you call it a net. You think of it, it kind of looks like a fishing net or whatever. But when you're done actually drawing something, it won't have all of that because you're using tracing paper, so that when you're done, you have a cleaner image that just has some lines or curves or dots on it, and the outside circle that gives orientation. This is a special kind of projection. So I'm going to walk you through kind of a cartoonish version of what's going on and how this works. So imagine you're really big and you have a globe and you have a cool, powerful laser beam. So you take something and you slice the globe right in half and slide a giant sheet of paper in at the equator, stick the globe back together. That paper is your piece of tracing paper that you're going to draw this on. Then you go up to the North Pole and you set up your laser that's so powerful it can blast all the way through the Earth and come out wherever. And it's always going to be at the North Pole. You're going to aim it at something because there's a tree in Australia that really pissed you off last week, and you're going to blast it with your laser. So you have your laser at the North Pole, and you shoot that tree. It's going to go through your paper somewhere. And it's a very specific spot on your paper. And so that point on your paper represents that spot in 3D space where that tree was in Australia. If you blasted something else, you'd get a different spot on your paper. So every spot on your paper represents some place in 3D space. And what you're representing, more than a line from the North Pole, is actually, we're basing it all off of lines that go through the center of the Earth. What I mean is, you have your laser beam up at the point marked zenith. You zap the tree, which is at point P, and get a P' hole in your paper. But Mathematically, what we're worrying about more is the line that goes through the dead center of the core and goes through the P. And so then we could do trigonometry on it and do calculations, which, because we're doing this graphically, we don't have to do. But that's where the proof of all of this working comes from. Now, if instead of just a tree at a single point, we're worried about a plane, like a bedding plane, or the limb of a fault, or not a fault, limb of a anticline, or the plane of a fault, all kinds of different things that we have in geology, we can imagine mathematically that the plane expands infinitely. So it's going to cut through the whole globe. Slide it so it goes through the origin, the center of the Earth, and we'll see something like this, where it's a big enough plane now, it goes through the edges of the Earth, and the Earth makes a circle on that plane. And it's called a great circle. It's called that because it's the biggest circle possible from the Earth. If we take our laser beam up at the North Pole and we trace that circle, so here's where the Earth is drawing that curve on this tilted plane. Whoops. Okay, I've got microphone back again. So I was saying, that specific curve is unique to a plane at that angle and that orientation. So now instead of trying to draw something in 3 dimensions, we can have that arc in our circle, and we know exactly what the orientation of the plane was that we drew. And by the end of the lab, you'd be able to look at that and say, okay, this plane has a strike of about 25 degrees northwest, or north 25 degrees west, rather, and is dipping at about 65 degrees. And I can see that from that arc that's in that third image there. So this is just kind of getting it a little bigger so that everybody can see it better. Now, if a plane didn't go through the center of the Earth and we actually drew it exactly where it was located, instead of a great circle, we would get what are called small circles. Pretty straightforward. They are smaller than the great circles. But we're not going to do those. The math and usage and drawing behind it is more complicated, so it's better to start with the great circles and learn the basic general use. So what can we use it for? Well, we can show a bedding plane if we have the strike and dip. We can show the orientation of cleavage on that bedding plane, on an outcrop, on a road cut. After next week, we'll be able to actually figure out the true dip of a bedding plane if all we have are a couple of road cuts with a parent dip. Much easier to do with one of these. It'd take you like 3 or 4 minutes rather than figuring out the trigonometry and making assumptions and trying to calculate it. We can show the orientation of faults and slickensides. We can find the strike and dip if we have a parent dip. We can show bearing and plunge of oil wells in an oil field, of other things, and many, many more uses for it. Fortunately, the basics are nice and basic as long as you have them explained in a nice way. So some of this setup is already done for you, basically steps 1 through 4, or 1 through 3 anyways. So you take a piece of cardboard, cut it out, roughly square, take your stereo net, stick it on there, already done for you. Then you need to take your tack and stick it through the dead center. Do it from the front first so you get a hole instead of guessing where the center is from the back. But then you'll have to take the tack out and stick it through the back. So it's basically sticking up through the center of your stereo net. This gives you a pivot point. I do have tape here. If your tack is falling out, you can throw a piece of tape across the back of it. For the folks doing this at home, there'll be a stereo net for you to print out. You'll have to find your own piece of cardboard and thumbtack and tape. I can't give you any. Yeah, sorry. So then take your piece of tracing paper, and you'll take your piece of paper and stick it over your stereo net, which means you're going to have a hole in the middle of your tracing paper. Tracing paper tears really easily. So you can do it just being careful not to tear your paper. Or once you've done it and you have a hole, lift it off, put a piece of tape across the back side so that it doesn't mess up any lines you draw, and then stick it back on. The tape won't tear as easily. It'll help your paper not get ruined. Then you're all set to actually draw on it. The first thing that you always have to do for a stereo net is trace the outside of the circle. It's called the primitive, and if you don't have that, your lines and curves have no setting, and so they're kind of useless. And you also have to mark the north, south, east, and west points on there, so then you know orientation. That's very important because otherwise it doesn't tell you strike and dip if you don't know which way is north. Most of you have a Sharpie. If you do the outside line with Sharpie, it makes it so it won't smudge. If you have to erase stuff, it doesn't erase your primitive. But other than that, don't use pen until you're all done and you know everything's right. If you choose to, then you can ink over your curves and lines and so forth. But not required, since this is for a lab. It's not for something that's going to be archived for 50 years. So at that point, you're ready to actually do something. Now, don't draw this one that I'm going to tell you about. You'll be drawing the ones from your lab assignment. But if we had a strike and dip, like south 80 degrees west, 40 degrees north, it could be an azimuthal. It could be, since this one is south 80 degrees west, we could also say that's north 80 degrees east. It's the same line. It's just the other end of that strike dip line. But so since it's in this format, we would start from the south pole, count 80 degrees along the outside, along the primitive, and put a little tick mark there. Then that's one end of our strike line. Now we can put the other end of the strike line, the north 80 degrees east, and we can put our dip line, north 10 degrees west. Who knows how I got that number? Because it doesn't tell me there. It just says 40 degrees north. So why am I putting a tick mark at north 10 degrees west. What do we know about dip direction? Perpendicular. Dip direction is always exactly perpendicular to the strike line. So north 10 west, oops, that should be north 10 east. That is a typo. North 10 east. No, it is not a typo. I am just really flustered, apparently. Yes, north 10 west is 90 degrees from south 80 west. Sorry. So that gives us two lines on exactly opposite sides of our circle, and then one that's halfway between them. Now, you want to rotate your tracing paper on your stereo net until that first tick mark is at either the south or the north pole. Doesn't matter which one. They'll both work. That'll put your dip direction mark on exactly either the east or west end of the equator, and your other tick mark at exactly the other south or north pole. If they don't line up like that, you know that you counted wrong somewhere. Then, from that tick mark that shows your dip direction, you'll count in along the equator 40 degrees. In your case, since you have lines every 2 degrees with a bold line for every 10 degrees, you would be able to count in 4 bold lines right along the equator of your stereo net. You'll be on a curve. Trace that curve from the north pole to the south pole along it, and I will show you what I'm talking about here. So we've marked south 80 degrees west, north 80 degrees east, and north 10 degrees west. We rotate it here, so my first one is at the south pole. My dip direction is exactly on the west end of the equator, and my other tick mark is right at the north pole. So I actually counted them correctly, and they're where they should be. I count straight in along the equator. There's 1 bold line, 2 bold lines, 3 bold lines, and 4, so 40 degrees. I trace that great circle arc all the way from the north pole to the south pole. Now the only thing left is to turn my paper so that north is back to north, and leaving it on the stereo net, it'll look exactly like this. You could take it off then if you don't have any more to draw, or you can, once it's oriented correctly again, you can go on to your next strike and dip and so forth if you're going to have multiple curves or other things on there. I made it go to the south. You could make it go to the north, just as long as it goes to one of the poles. And so that lets you display a bedding plane from 3D space on a 2D piece of paper. And as soon as somebody is comfortable with using these, they'd be able to look at that and know exactly what orientation, what the strike and dip was, and be able to picture that plane in 3D space. Basically, if that's north over there towards the door, this is a bedding plane about like that. No, that. I had it off by 90 degrees, sorry. So just like that. If the curve was something else, maybe it would be this plane or this plane and so forth. So basically part 1 is doing this kind of thing using strike and dip and drawing the curves, the great circles, for the bedding planes. The other thing that you're going to learn to do today is the linear features. Now you might be given bearing and plunge. All that is basically a direction and then what the dip angle is. So this doesn't have any strike line. So if it says 0 degrees north, then it means that the linear feature was facing exactly north. If it says that the plunge is 25 degrees, it means it's dipping down 25 degrees into the ground. The strange thing about bearing and plunge is you always call it bearing and plunge, but it is always written plunge first. Otherwise, if we didn't do that, it would look like it was a strike and dip. I'll give an example in just a moment. Oh, actually, I guess it's on this slide, sorry. So in the example at the bottom here, 45 degrees is the plunge. North 71 east is the bearing. So that's important when you go to do these. If it says that it's a bearing and plunge, the second number is the bearing, the first number is the plunge. Rake. Has anybody actually heard about rake before in geology? It's not a term that comes up commonly, but I believe I've got an image here. This bottom left image looks like something you've seen before, right? When talking about faults. Well, that angle there, theta, the actual direction that the fault moved when it was, a normal fault in this case, is the rake. If it moved basically straight away from us as more of a transform fault, that would be a rake of 0. If it moved straight down, no lateral movement at all, that'd be a rake of 90. And then if it moved straight towards me, towards the left, that'd be a rake of 180. So anywhere in between there, you have some rake angle. The linear striations that you can see could be measured because they will match that movement. You may have linear minerals or other things caused by those stresses. The myelinites might be lined up like that. And so you can use that rake angle, or you could use a bearing and plunge, depending which one's reported to you. On the right here, we can see an anticline that's plunging, or at least an antiform. We don't have ages of the material. So we have a plunging antiform. And that plunge, that hinge line, has a direction and a dip angle. So it has a bearing and a plunge. So how do we draw these linear features on a stereo net? Well, if we're given a bearing and plunge, we make sure that we recognize the south 42 west is our bearing. And we have our primitive, mark the northeast, south, and west, exactly like you were preparing for the other one. And then we'll count 42 degrees west of the South Pole and put a tick mark, just the same way we started previously. We're going to not worry, no other tick marks. Immediately turn the paper until that tick mark is at one of the poles, North Pole or South Pole, your choice. And then count along that north-south pole line 38 degrees. That's the plunge. So in this case, we made our mark. I've already turned it, so the 42 is at the south. And then I counted up 38 degrees. And I connect it, that 38 degrees in with my tick mark, and it gets a double-headed arrow. So it's a little hard to see here, but at both ends of the line is a little arrowhead. That helps identify it as a linear feature. It's a bearing and plunge. And then when you're done, spin your paper so north is north again. And that line right there tells you what the bearing is by where it is along the outside of the circle, and exactly what the plunge is by how long the line is. If we have rake, it's a linear feature on a plane. It's, the striations on that fault plane, for example. So we're basically combining the great circle for a plane and a linear feature. So you draw your great circle following exact same steps as you did in part 1. And then you want to rotate it so that your great circle is curved to the east. You know, when you did it initially, it might be curved to the west, it might be curved to the east. But to draw the rake, you need it to spin it so it's curved to the east. Then count down from the North Pole along your arc, not along the outside, but along your actual arc that you drew, the number of degrees that you were given for the rake. So in this example here, like I would have started with this point right here at the North Pole and counted down that many degrees along my circle. And I put a little dot there. Then I spin it until that dot is on the north-south pole of my stereo net. And then draw from there to the edge. All done. So very straightforward way to do it as long as you remember what you're counting along and always rotate it back so north is north before you do your next thing. So we won't do it. That's all you have to do on this lab today. Those two kind of tasks. So I will put it back. These directions are on your actual lab handout for the rake. So I will flip it to leave these up.